Very warm welcome. We are talking about solid state in this series on NCERT. We are discussing NCERT and I present to you solid state. This is Shishir Mittal from Vyas Certification. Let's begin. Define the term amorphous. Give a few examples of amorphous solids. What exactly is amorphous? Whenever solid substance is there in which individual particles have no systematic order. No systematic order means none of them must be ordered. Actually, they could be ordered for a short range. It is not necessary. They may be, they may not be. But at least long range order must not be there. If that is the case, then these are called amorphous solids. So amorphous, as you can see, amorphous means no form. They have no systematic crystal structure. So particles of irregular shape. I mean, that's not very true. I would say rather particles of irregular arrangement, because they all could be having identical shape and that is also perfectly okay. Irregular arrangement. Could I not have corrected this before writing it? I could have. This is an intentional gap so that I can highlight that these are the common errors made by people, and especially the students. The arrangement of constituent particles in such a solid has only short range order. This is also a kind of misconception. It kind of makes it very necessary that there has to be short range order. No. The truth is they may or may not have any order. If they are totally disordered, they are amorphous. Even if they have short range order, don't start calling it that they are ordered, they are ordered. They are not ordered, they are still amorphous. They will be crystalline only if there is a long range order. There may be a short range order. It's not compulsory, it is optional, right? In such an arrangement, a regular and periodically repeating pattern is observed over short distances only may be observed. What I am giving you is a very popular answer, the way it is written, and why I am modifying it, because that should be the answer, right? So I hope you get this. Examples are very common. If you take a plastic, if you take rubber, if you take glass, they are classical amorphous materials. If you want point-by-point comparison between crystalline and amorphous solids, well, this is what we have. You could talk about the shape, melting points, cleavage property, enthalpy of fusion, isotropic nature or anisotropic nature, and arrangement of constituent particles. These are various points on which you can compare crystalline and amorphous. Like crystalline solids have a very well-defined geometrical shape. Amorphous may not have that, right? But please remember, individual particle, if it is very regularly shaped, still the overall solid may be amorphous only because the arrangement in which those particles are there may not be very regular. Sharp melting points for crystalline solids. Amorphous solids have a range of melting points. They don't have a sharp melting point. That is the most characteristic defining property or distinction between crystalline and amorphous. And if you're trying to cut crystalline solids with a sharp tool, imagine taking a sugar crystal and you're trying to cut it with a knife. No, you would find it is difficult to cut, and if you break it, if you hammer it, it cleaves around plain irregular surfaces. I mean, you can't just shape it like, if you're carving with a knife, if you're, say, for example, carving wood with knife or you're carving plastic with a knife, you would find that you can carve it in whichever shape you want. In crystalline, because they're amorphous, in crystalline solids, you can cut it slightly, but the moment you make a small cut, the remaining portion breaks away on its own, giving you a plain surface. And that is which makes carving on these solids a little more difficult when they are crystalline. Enthalpy of fusion, if they have sharp melting point, they have well-defined enthalpies of fusion. Amorphous solids don't have sharp melting points, so obviously they would not have well-defined enthalpies of fusion. They could, they could take different heats in melting, kind of. Anisotropic. Crystalline solids are anisotropic. That means all their properties, if any property at a given point is measured in different directions, you find that that property, depending upon direction, could be different. Even if a single property exists, which at a given point, if it is measured in this direction or this or that, is different, you would find that the solid is called anisotropic. Isotropic solids, they have all similar properties. That's the case. I mean, the properties, whichever property you try to measure, in one direction, in second, third direction, the property will be measured to be same. Sometimes crystalline solids are called true solids, amorphous solids are called pseudo-solids. Even supercooled liquids is a very fancy name which is given to amorphous solids because they don't have a long range order. So they may not have an order or they may have a short range order, while crystalline solids always have a long range order. These are so many points of distinctions between crystalline and amorphous solids.